I'm introducing a model for friction, which is one of the trickier forces to deal with, I think, in basic physics. There's two types of friction that kind of comprise this model. One is kinetic friction, and the other is static friction. This model was originally discovered by several different people, but is sometimes referred to as Coulomb friction because he was one of the discoverers of some of the main components of this model. Anyway, the two components that are here, kinetic friction, I want to talk a little bit like what does that mean? Like what is friction in general? Well, we know friction is generally between two objects, right? They're two objects maybe rubbing against each other in some way. Maybe it's an object that is sliding over the ground. Maybe it's like a brake in a car or something like that, right? That's got a sliding on a brake rotor or something. Generally speaking, friction has to do with the interaction of two surfaces. Now, we're identifying two different ways that that can happen. One of them is called kinetic friction. And the amazing thing about kinetic friction is you can actually write a formula that relates the magnitude of that friction force to the normal force at that surface by a coefficient. So this is really force of friction is equal to kinetic coefficient of friction times normal force. I say it's amazing that we can have that equality because this doesn't reference things like, well, how fast? Like if this is an object sliding over the ground, does the force of friction depend on how fast the object is moving? And the answer is no. All it depends is how hard that object is pushing on the ground, maybe due to its own weight, although I didn't say the ground was necessarily level, did I? Because then it may not be its own weight. Things can get more complicated in that sense. To help us, though, conceptualize, like when do you know you can use this formula to deal with friction, and we'll see some more examples of that as we go forward. I look at this one as the slipping case. So if you have two surfaces and they are slipping against one another, or there's some kind of sliding, which really means they're slipping, then you know you're in the kinetic friction situation. A pitfall that I've encountered is sometimes one will assume that because it has the word kinetic, that simply if an object is moving, either as a result of friction or with friction being there, that that automatically means that there's kinetic friction. And a counterexample I have to that is like imagine an object, maybe like a heavy box or something like that, sitting in the back of a truck. And if the driver accelerates moderately, it turns out it's actually the static friction force that makes that box accelerate, provided that it is not slipping. So that kind of brings me to this this second one, the static friction, which is given to us as or presented to us as an inequality. It says force of friction is less than or equal to static coefficient of friction times the normal force. Something worth noting, by the way, in the formulas I wrote here on the whiteboard, I subscripted them the same, both of them as force of friction, whereas here I said F sub k for kinetic friction, here F sub s for static friction. But really, you know, what's in a subscript? There's no one way to do them. I wrote them this way here because in problems, usually that's what I'm going to wind up do, whereas on this slide, I wanted to clearly distinguish the kinetic from the static cases here. The static case, if you wonder, like, well, how do you know it's static? Instead of wondering whether the object is moving or not, ask the question about slipping, and I'm going to label this one with a no slip. So like you can have that box in an accelerating truck, and as long as it doesn't slip, there is static friction between that box and the truck bed that it is resting upon that is making it accelerate up to a maximum. So in that sense, if you say like, well, why would this have to be an inequality, right? So like if we thought about that, I'm just going to draw like a flat surface here, maybe representing the back of a truck, and here's like a box in it, right? And if the truck only accelerates a little bit, there'd be some acceleration here for the box. And if I were to kind of think about like, well, what would be the FBD for this situation? I would definitely say, well, there's going to be some static friction force responsible for that acceleration. And in terms of the other forces, naturally the box is going to have a weight and it's going to have a normal force. And so if you ask like, well, what governs this friction force? Generally, in all cases, it's this normal force. In other words, how much is this object pressing on the surface that it's sitting upon governs how much friction there could be. If the box is sliding, it's given by this equation. If the box is stationary, it's given by an inequality. In that sense, if the truck is just cruising along and there's no acceleration, force of friction is probably pretty close to zero, if not exactly zero. If the truck is accelerating moderately, maybe the force of friction is like half of what coefficient times normal force would be, or maybe even a third or whatever. But now let's say the truck, probably the most extreme situation in reality, if the truck slams on the brake, right, or on the brakes, this box might, it's conceivable, right, could wind up sliding forward as a result of that. And that generally happens when the amount of friction that's being required there, or that would need to be there for the box to stay stationary, exceeds, instead of being less than or equal to coefficient of friction times normal force, it's larger than that, which can't happen, and then it loses traction, the box slides. And that can happen in other situations as well. All of this, though, like I said, falls under this kind of heading of Coulomb friction, or just friction if you like. These are models. It's not really like a fundamental force, is maybe one way of putting it. Like, although I don't know, we haven't really looked at fundamental forces that much in this class, like fundamental versus not fundamental versus empirical, you could say. This model, in that sense, is just an empirical model for friction, and it's not perfect. So an example of how it might not be perfect is if you left an object sitting in some spot for 10 years, and you ask, is the coefficient of friction going to be the same if nobody touches it 10 years later? The answer is no. That object might be stuck there now. That is something that kind of like leaps outside of what these equations and inequalities can tell us about. So it's worth recognizing this is a model. This coefficient of friction is part of this model, but it is not like fundamental. It is not like always going to hold the same in all cases. Sometimes there will be things get stuck in some way just because it's been sitting there for long enough, and that's one of the common examples. These coefficients of friction is maybe also worth talking about for a second, because, like, you know, where do you get those? What values do they have? And the answer is that it really depends on the two surfaces and generally what material they're made out of. So, like, if this box is made out of wood and sitting on metal, there's a coefficient of friction for that. And it may also depend on what metal it is. It may depend on what wood it is. So you can look, nowadays there's a lot of online resources where you can look at really lengthy tables of common coefficients of friction, particularly for engineers may be interested in that. There's some that I like to use that are kind of like made for engineers to use. But it turns out there's a lot of coefficients of friction out there. So it may be like if you're getting very, very specific, it may be hard to find a value. Maybe you have to do like an experiment to find what it's going to be. Generally speaking, though, coefficients of friction most often will have values up to 1. Very rarely you see values that are larger than 1. Another truism that tends to be there is that kinetic coefficients of friction tend to be smaller than static coefficients of friction. And one little thing I'm just going to mention, I want to end this video soon here, it's getting a bit lengthy. But if you ask, like, why are there such things as anti-lock brakes? And the reason why is that the capacity that static friction has to, say, stop a car is higher, because this coefficient of static friction between the tires and the road will tend to be larger than the kinetic coefficient of friction, beyond the fact that you might lose control while you're sliding anyways. But the other fact is, if your tires are not sliding, your braking distance will be shorter because of that larger coefficient of friction.